Good afternoon, everybody. My name is Matteo Romano. I'm a PhD student in aerospace engineering in Polytechnic Milano. Today I'm presenting the new approach we are developing for planetary protection for interplanetary missions in the framework of the COMPASS project, which is a ERC-funded project, together with Camilla Colombo. Okay, I'm going to give a short introduction on what is planetary protection and why it's important, and then focus on the two main parts of the presentation, which are about numerical integration and Monte Carlo sampling. And planetary protection is a phase of the design of space missions that aims to avoid the collision of spacecraft and debris and launcher stages with planets and moons that are valuable targets for biological research in order to avoid the contamination of these bodies. This is done by ensuring that the probability of collision of these trajectories, of the trajectories of these bodies, is very low. It's below some thresholds that are imposed by international requirements. And there are actually many factors that are involved in this. The main ones we are focusing on are the uncertainties of the initial state and the uncertainty of the design parameters of the spacecraft, but also some random events like failures of propulsion system. And the starting point of this work is Snapshot, which is a numerical tool that was developed by a team in the University of Southampton for numerical analysis, the numerical analysis of planetary protection for the ESA. I want, here you can see the structure, but I want to focus your attention on the two main parts here, trajectory propagation and Monte Carlo, because they are the ones we are focused on in our initial approach in order to understand how the errors of the propagation can affect the analysis of planetary protection and how to find new techniques that sample more efficiently the initial distribution of the spacecraft. So for the numerical integration, we are trying to counteract the accumulation of numerical error during the propagation in order to make more accurate the estimation of the state of the spacecraft. This actually involves some numerical approaches, some alternative numerical integration techniques that we are focusing on. For example, symplectic schemes to ensure the conservation of the total energy, but also some other numerical techniques that also take care of, for example, the numerical error that are introduced by flybys, because in planetary protection also important the conditions of resonant orbits that are caused by flybys. And this is an overview of the numerical methods we analyze. Snapshot already implements the Runge-Kutta methods, the adaptive Runge-Kutta methods, and so we continued on the Runge-Kutta family with some others, also symplectic schemes. For example, the implicit Gauss-Legendre Runge-Kutta, or the Runge-Kutta-Nystrom for separable Hamiltonians. But then we also looked at some other schemes that are derived from the Hamiltonian formulations with the canonical transformations. And then you can see here which were implemented, and especially their properties. You can see that the symplectic ones here are all formalized with a fixed step approach, but some are implicit and some are explicit. And this actually comes into play when considering, for example, in this example, there is the propagation of Apophis up to 2029, just before the flyby of Earth that is expected. You can see that both techniques, symplectic and non, actually give comparable accuracies. Here you can see the errors in position and velocity, and the variation of total energy, which is, as expected, conserved during the propagation by symplectic methods. But while this spike here is caused by close approach, I will come later to this. And some other techniques that we analyzed were focused on making more precise the tracking of the dynamics, for example, with the step regularization, but also considering that since the symplectic methods we analyze are formalized with a fixed step, this actually removes the symplectic properties, and also some other projection methods that correct the numerical solution with according to the gradient of the energy function in order to minimize the error of the energy or any constant of motion at the cost of including an implicit nonlinear problem to the computation cost. But I spoke about flybys before. This is actually the main problem of the main issue. You can actually see here that this is again a office, but with the propagation also including the flyby of 2029. You can see
there should have been a flyby also in 2013, no? The evolution of office, which was important.
These
don't have such feature.
these are the. This is compared with the propagation of new horizons. This is probably the close approach I was speaking for. You can see the spike.
Surely there will be in 2029, but
it's true that we also obtain similar plots even considering that because this is yes, there is, but not so strong like this one.
No, probably if I can do just better, and then probably is this no wait. It is around here, so it's just a close approach.
Can be seen in
yes.
the
No, in fact, this is just probably just a close approach that doesn't affect so much the behavior of the integration, like a flyby, a very close flyby like this one. And so the problem is here to counteract the effects of this flyby that, in general, of flybys. This is done with many possible solutions. For example, some switch the center of integration once for example, the Earth in this case is reached, but we also try to, for example, include the projection techniques to correct the energy during the flyby. But anyway, all these methods actually have the required to identify in an accurate way the condition of flyby, what a flyby is during the propagation, possibly in an autonomous way. And this can be done by setting, for example, a distance from the planet. We tried with another approach by also looking at the behavior of the dynamics through the Jacobian, through the value of the Jacobian, by looking at the eigenvalues of the Jacobian, and in particular to the contributions of the single planets with respect to the main attractor, in this case the Sun, while considering only the value of the eigenvalues. One can obtain a definition that is similar to the definition of sphere of influence of the planet. We also look at the time variation of this eigenvalue in order also to include the approach velocity to the body, and this can be done by considering them separately or by looking at the combination of these two conditions. And this is all for the integration part. While for the sampling techniques, again starting from a snapshot, the tool already implements a Monte Carlo approach that selects the number of runs depending on the confidence level that is given, on the desired confidence level that is indicated. While for this point, we also considered some other methods that are based again on the Monte Carlo approach that aim to increase the accuracy or the efficiency of the probability estimation. In particular, I'm going to explain here the line sampling, which is a sampling technique again based on Monte Carlo that uses lines instead of points to probe the uncertainty domain and identify the boundaries of the impact region. This actually was developed for this was a method that was developed initially for the study of failures of complex mechanical systems, but we applied this, we adapted this one. The part of identifying the boundaries of the impact region can be done autonomously from the initial uncertainty, and then use later the information that has been found to obtain an approximation of the impact probability. However, this is done for efficiency. And this probability is actually computed analytically thanks to integration. I will explain later. Now, just a quick explanation of how the methods work. The first part is to determine a reference direction that will be used for the line sampling. And this is done by obtaining some information in different ways, for example, with the Monte Carlo run or some optimization process about the impact region, and so that this reference direction can point toward the impact region. This is a very important step for the line sampling, since this is a very important step for the line sampling, as I will explain later. And after this, new samples are generated, new initial conditions are generated according to the distribution that is given by the problem. And then they are mapped inside another coordinate space that assigns to every coordinate a unit Gaussian distribution. Again, this is a very important step. This transformation preserves the cumulative distribution function between the two coordinates, between the two distributions. The sampling is done by defining lines for each sample that will then cross the impact domain, and the main goal is to find the values, the points on these lines that correspond to the boundaries of the impact region. This actually is done with an iterative process that requires extra orbital propagation. We expect more orbital propagation than initial conditions. But once all the boundaries of the impact conditions are found, of the impact region are found, the total probability is computed as the average of partial impact probability along each line. These partial probabilities are found analytically thanks to the cumulative distribution function of the unit Gaussian. This is actually why this method uses the transformation of coordinates in order to consider this integral analytically. Just to show you the application, this is the analysis of the flyby of Venus of the launcher of the Solo spacecraft, which is under development at ESA. You can actually see here in red the impact region that is found through the Monte Carlo and standard Monte Carlo, and in green the boundaries that are found thanks to the line sampling. However, you can actually see that in this case, where a very large probability is expected, around 4%, the two methods give a similar confidence level for this estimate, but the line sampling using an iterative process actually requires more time to run, but is actually an extreme scheme, an extreme example. And another example, another more favorable example, is the one of Apophis with the calculating probability in 2003 with the old observations of 2009. You can actually see that in this case, where this small probability is expected, and also this impact region is distributed around the uncertainty domain, the number of orbital propagation that is also a measure of the computational time can actually be lower for the same, for a similar confidence level for the solution, but also we can obtain at the same cost here by using a same number of propagations. We can obtain a better confidence level. Now, to sum up, these are the same considerations I did while speaking. Now, for the future work, also at looking new numerical methods and also other techniques to make the sampling more efficiently. Our final goal is to apply those two approaches together at the same time for making planetary protection analysis more accurate. And this is all. Thank you for your attention. Are there any questions?
When you speak about non-synthetic methods, are Are you thinking about specific problems and specific methods also?
No, for now are just syntactic methods, just the ones that are already implemented into the snapshot tool that are the classic adaptive Runge-Kutta of high order.
I mean the non-symplectic.
Yes, the non-symplectic. Those are the non-symplectic ones.
Any other question? Let's thank the speaker again.